already get started. All right. Good afternoon. Good morning, everyone. Welcome to our first inaugural webinar series for SCALE, Southeast Consortium for Assured and Leading Edge Semiconductors. It is my great pleasure. We have great two industry leaders in advanced packaging integration. And let me briefly introduce our speaker today. First speaker is Mr. Alan Huffman, who is currently Senior Director for Heterogeneous Integration Business Unit at SkyWater. He has 27 years industry experience. And prior to joining the SkyWater, he worked for Micros, RTI, MCNC, and he had a BS degree in physics and University of North Carolina, Chapel Hill. And he is a technical focus as a heterogeneous integration, advanced interconnect technology through his career. Thank you, Alan. And we have another speaker, Dr. Chuck Woychik. He is currently Director of Advanced Packaging Platform at the SkyWater Technology in Kissimmee, Florida. Prior to joining the SkyWater, he used to work for i3 Microsystem, 3D Technology, GE, and IBM, Endicott, and New York. And he has expertise in material and processes for electronic packaging. He holds a doctoral master's degree in material science engineering from Carnegie Mellon University. And he had presented numerous research and conference and has a publication, also 120 issued US patent. So let's welcome our speakers, Alan and Chuck.
Thanks, YK. I will go ahead and share my screen now. Hopefully you'll be able to see this. Is that coming through well?
Yes. Yeah.
Okay.
Thank you.
Great. So again, thanks for the introduction. So Chuck and I are going to do this in tandem. So I'm going to take the first part of this discussion and then hand it over to Chuck midway through. This is a presentation entitled "Don't Forget the Package," and we are kind of talking in this about the larger picture of how the United States is looking at establishing domestic heterogeneous integration capabilities and some of the thoughts that SkyWater has around this, both from the larger U.S. ecosystem perspective and some of the capabilities that we see that are very important to this, and where SkyWater is engaged in trying to put together some solutions for that ecosystem. So starting with this group of headlines that I've just blatantly plagiarized from a number of different news articles over the past several months. And I'm sure all of you have seen a lot of different headlines that are very similar to this, where large fab facilities and companies are planning on growing their fab capabilities here in the United States and putting in leading edge foundry facilities. Not only just the big companies like TSMC and Micron and Intel, but also you'll notice I put in here the one for SkyWater, because we're planning to do the same sort of thing in Indiana in partnership with Purdue University. And there's been a lot of attention about this fab expansion capability, and certainly as the CHIPS era gets underway, there has been more focus on the fact that an advanced packaging and heterogeneous integration capability needs to also accompany this. So if we kind of look at this from a holistic view in US semiconductor manufacturing, what's happened over the last several years, you see some trends here that are certainly troubling, and a lot of what the CHIPS funding is intended to help address. We've seen the US contribution to the global semiconductor manufacturing capacity drop fairly precipitously over the last 30 years. We're at about 12% today in total semiconductor manufacturing capability. We've seen a lot of governments around the world that have invested heavily in supporting semiconductor industries in their own countries. And so that, coupled with a lot of cost consciousness manufacturing decisions over the last 30 years, have resulted in a lot of the global manufacturing capacity for semiconductors now residing in Asia. And that includes nearly all of the leading edge technologies in CMOS fabrications, as well as in advanced packaging capabilities. The last few years of the COVID pandemic, we've seen a lot of the vulnerabilities that this existing supply chain can have, shortages of parts, the geopolitical concerns that have come out of this as well. And this has really highlighted the need for a more well-established U.S. manufacturing capability in semiconductors. But this has been a concern for a number of years. Not just from the supply chain side of things, but also from the security and national security interest and technological superiority. It's a pervasive issue that has really far-reaching economic consequences. We're all aware of the ubiquitous need for stable and secure supply chains. So if you look at things in the consumer industry, shall we say, there's been a lot of focus on automotive aspects of semiconductors over the last couple of years, and the shortages that contributed to short sales in automotive supplies. Consumer electronics has certainly been a focal point, but there are other areas that are very important from the security perspective, and being able to establish and vet the supply for semiconductor components. The banking industry is one. The utilities industry is one that doesn't get really talked about very often. You have cloud computing and big data capabilities that need a lot of security. And of course, for industrial applications, the security within industry and individual companies is important. It also is no surprise that there's a defense and national security need in all of this. And this is the slide that some of you might have seen before. It was originally presented in one of the DoD Trusted and Assured Microelectronics meetings a few years ago by Dr. Moldavan, but you see a lot of the focal areas here that depend on microelectronics technology from a national security perspective. Cyber and quantum technologies, mesh networking, artificial intelligence, directed energies in space, and hypersonics are all very important market spaces. We have a continued reliance on non-US microelectronics for a lot of these systems, and that creates supply chain and security risks for the nation. And it's also well known that the volume requirements for these applications are certainly smaller than commercial markets. And so this creates problems for the government in terms of accessing leading edge technologies at a low volume point, but with cost and security concerns. So it's often not possible for us to establish the security requirements with existing commercial providers. There have been instances in the last several years, for example, where previously aligned companies with DMEA, for example, were not allowed to continue to do security audits. So that creates a question about the security provisions for our national security needs as well. So a lot of factors that come together to motivate us as a country to begin to onshore some of these technology capabilities. Specifically, we look at just packaging here in the United States. Certainly over the course of my career, it's been one of the things that we've seen ebbing away from the United States for a number of years. Current estimates in the industry right now put the U.S. contribution to global semiconductor packaging at about 2 to 3%. We have no major OSAT companies with manufacturing operations in the U.S., though we have engineering and sales and management operations here. We have a number of companies here in the U.S. that have prototype to low volume capabilities, and they support a number of advanced packaging and heterogeneous integration technologies. And those companies have business models that are well established to support both government and commercial business opportunities, but they're not high volume manufacturers today. And so now that we've really kicked off the CHIPS era here as starting yesterday, the majority of that CHIPS funding, as I'm sure you're all aware, is going to look at supporting front-end device fabrication manufacturing. Now that the ground rules and the methodologies have been established and announced by the government, we see that they're actually going to be focusing on leading edge technologies first and legacy technologies second. But there is going to be a significant effort that's going to be focused on the development of our advanced packaging and heterogeneous integration manufacturing capabilities as well. To wit, it doesn't do the U.S. a lot of good to have leading edge semiconductor capability if we don't also have leading edge packaging capability. So there are a couple of program initiatives that are being established under the program, the CHIPS program, that are going to impact the U.S. packaging picture. There is the Department of Commerce's National Semiconductor Technology Center that's going to be established as a public-private consortium that's going to support R&D and prototyping for advanced semiconductor technologies. And then there is the NAPMP, the National Advanced Packaging Manufacturing Program that NIST is developing, and that falls also aligned with the NSTC with a directive to support up to 3 manufacturing USA institutes. If you look at the funding that's been allocated from the CHIPS Act for these efforts, you see about $4.5 billion in the first year that is going to go to NSTC and the NAPMP. Those are going to be initial larger quantities in the first year for the establishment of these programs, to set up these program offices and to get programs underway. And then you see about a $6 billion expenditure that's going to be happening for those initiatives over the next 4 years. There are a couple of organizations, relatively large industry organizations, that have been working on preparatory activities around how we could structure the NSTC and NAPMP and collaborate over a large group of industries and companies. You see that the Department of Commerce received 200 responses to to their request on feedback on how these funds would be used to establish the manufacturing capabilities. So you've had a tremendous amount of interest from companies here in the U.S. that are related to the packaging industry. And that all really bodes very well for being able to develop a very strong ecosystem of companies and capabilities under these programs. So when we talk about the advanced packaging ecosystem, there are a very large number of capabilities that are incorporated here. And while large OSATs pull a lot of these capabilities together under one company or on one roof in some cases, here in the US, a lot of these capabilities exist today, but they're quite widely distributed amongst a number of different companies. And so I wanted to kind of give you a brief overview of what I think are a lot of the important aspects of this advanced packaging ecosystem. And it just shows the breadth of capabilities that need to be brought to bear here in the US at higher volume capacities as we look forward into reestablishing more manufacturing capability in the US. The US has traditionally been quite good at the design side of things. We're a design leader in terms of EDA software and in terms of multi-physics modeling. And all of those are actively being worked on in the packaging arena to develop assembly development kits and design capabilities that are customized to the capabilities of providers in terms of their packaging architecture offerings. I'm going to skip over substrates for a moment because that's an area of tremendous concern here domestically, because we don't really have any substrate providers to speak of at high volume. We do have quite a lot of capability in physical interconnect here. Again, a number of smaller companies who can support things like WLCSP and C4 wafer bumping, copper pillar, and direct hybrid bonding, but no real high-level manufacturing capabilities in the U.S. today that are not already captive. There's a lot of back-end process capabilities with small companies who can do wafer thinning and dicing and singulation and provide die-level services. But again, no large manufacturing capabilities. Same thing for assembly. A lot of advanced capability, but nothing that's really been leveraged into non-captive, open source assembly capabilities beyond a couple of contract manufacturers here in the US. A lot of discussion about testing and how we're going to be testing these different technologies, these different HI approaches, which become much more difficult for us to do at component level now that we're integrating things much more closely together. And then there's a lot of additional aspects of this ecosystem too that come into the materials providers and the equipment providers. Are we going to put security protocols on top of these facilities, particularly when they're supporting top secret applications for the government, for example? And then there's the pervasive question about workforce that we have, and the recognized need that the United States will have in terms of developing a lot more people who can contribute to the semiconductor industry than we have available to us today. And one of the important things that's going to come out of that workforce as well, particularly as it relates to applications and companies that are going to support the government programs, is how many U.S. citizens do we have that are going to be able to support these programs, and how do we implement the security requirements around those programs that are needed in these organizations that are serving both commercial and government applications. So it's a really very wide ecosystem of capabilities. And while there's a lot of distributed and low volume capability, there isn't a lot of well-established high volume capacity. So at this point, I want to transition over to talk about what SkyWater is doing in this space, and I'll hand it off here to my colleague Chuck momentarily. But for those of you who are not familiar with what SkyWater is doing today, we are the first US-based pure play service provider of silicon interposer, fan out, and hybrid bonding technologies that we're establishing in our facility in Kissimmee, Florida. This is located at a development park called Neo City, which is being supported and funded by Osceola County. SkyWater and Bridge are in a partnership right now to develop these technologies together. We have an ongoing program in silicon interposers. Fan out and hybrid bonding technologies are things that we've added just in the last year. And all of this facility is designed to be able to support these 2.5 and 3D HI microsystem operations for both commercial and government customers. So we have established ITAR registered capabilities, but we're also going to be supporting commercial and non-government applications as well. So this is a very unique public-private partnership operation that not only is standing up capability today, but is poised to really expand tremendously over the next couple of years through some of the grants that we've been awarded here over the last few months in cooperation with the county and with Bridge to continue facilitization here, as well as some forward-looking program opportunities that we're engaged in to expand our capabilities even further. So it also is going to end up being a launching point for workforce development that we're engaged in with the county and with Bridge. It includes, the local universities within Florida, as well as a view towards collaborating with other universities around the country who are going to be engaged in packaging and HI technology research. So at this point, I'm going to turn it over to Chuck, and Chuck, I'll continue to push the slides forward for you.
Okay, thank you, Alan. So what I'm going to talk about now is our core platforms at SkyWater. The first one being the silicon interposer. So as was previously mentioned, what we are doing is work with Bridge, and this is based upon a license from IMEC technology. So the IMEC funded, the IMEC license technology is being used in this IBAS program to create these 4 different phases of silicon interposer. The first phase being a simple bridge interposer, and this activity is a 4-layer buildup structure, copper damascene, on a fully thick silicon interposer. A silicon substrate. This is fully qualified. It's available right now. So This leads into phase 2, which has the same buildup structure, but now we include a 10 by 100 micron TSV, and this will be fully qualified in the by the end of the second quarter this year. So what we'll have now is the phase 1, phase 2, a bridge interposer phase 1, and a TSV based interposer available by the middle of this year. And I just want to mention the finest lines are 1 micron lines on this interposer. This feeds into phase 3 interposer, which is shown in the schematic in this figure. And this gets into a more sophisticated buildup, more layers, but it will have a MCAP decoupling capacitor embedded into the buildup structure, along with the same size TSV, but it will have now a backside bump and a simple RDL structure on the back. So this will be a more sophisticated silicon interposer. And this will be target qualification for this will be by the end of third quarter this year. What we are also looking at, and phase 4 would be a low dielectric buildup structure, most likely a BCB in the top, with the same size of TSV bump and a more sophisticated RDL on the backside. This is targeted to be completed in the 2024 timeframe, and it's still in the process of being funded. So that's the target to get this completed in the 2024 timeframe. So really capacity and capability expansion in the future to support higher volume for these for our customers. So the key thing is right now, by the end of this year, we'll have all 3 for the first phases available for customers. Next slide, Alan. What this is showing is just the a core technology for a silicon interposer with a through silicon via, and this is just showing the capability that we have now at SkyWater, which is a blind via, so it's a bottom-up fill chemistry. And the important thing to show here is that what we get is a TSV with no seams, no voids, and you have the nice equiaxed crystal structure. So this is an important capability that we now have to enable the TSV-based interposers. Next slide, please. So if you really look at the technology details, they're outlined on the left-hand column. But the important thing right now is our chemistry is a electroplated copper, and we have the four metal layers copper damascene that we can build up. For the phase 3, it's a little more sophisticated, more layers. In the future, we want to have organic RDL structure, and I'll get into that discussion as we get into the DECA technology. So typically, as you well know, the backside RDL structure is typically a polyimide buildup type of structure, and that's what we plan to use on the backside for our RDLs, and it will also be solder bumped. In addition, what we are offering is a daisy chain and test vehicle. This is going to be a 30 millimeter by 40 millimeter silicon interposer, which is quite large, and it'll have 3 die that'll be solder bump attached on the top side. And as you can see in the back on the right-hand side, there's a schematic of the test vehicle. So there's going to be the daisy chain, which is really to get the bugs out of the process and also to do reliability testing. But it will be that larger format. So this is just showing this design will be built on a ceramic substrate. That's mainly due to our customer requirements. But we'll offer the reliability data, and then when the full functional module is built, the functional data for that. So in terms of the roadmap right now, the phase 1 is fully qualified. Phase 2 will be qualified by Q2. So really we're bringing in the 2 dates for phase 1 and phase 2. And the phase 3 will be qualified, really targeted to be qualified Q3 of this year. And then phase 4, the goal is to bring that really into we expect probably early next year, Q1 2024. So as you can see, by offering these technologies, we'll have the suite of reliability and functional data for the customers. Next slide, please. So this is a really exciting technology that we're in the process of bringing into SkyWater right now. It's really the DECA M series fan-out wafer level packaging technology. So really, if you look at this technology, the key thing here, it really gets into, it could be a chips first fan-out, fully encapsulated, but can also include a chips first and chips last. So there's many different variations of this. But the important thing with the DECA technology is that it has a capability to do adaptive patterning to accommodate die shift in the molded reconstituted wafer. And this is really important because what that allows one to do is to achieve a high yield, which can help drive down the cost to make it a very cost competitive package. So as you can see in these schematics right now, the single die, single RDL image on the right-hand side in the upper left or in the center just shows the basic construction. So you totally encase the die. In the structure, you have a copper stud plated on the die. That allows for a very nice planarization of that epoxy mold compound surface to do the sequential buildup. Of course, this is a simpler design, just showing one layer, and then you can do the UBM and solder bump it. The slide over to the right shows two die chips first kind of construction, and below that gets into a much more sophisticated design where you have a embedded die in the core, chips first die. But in addition, you have buildup layers in the top, 3 buildup layers in the top side, 2 in the back side, with a through mold plated via. And what this shows nicely is that you then can have a chips last, which is shown here, which is attached with a solder cap copper pillar in the top. And then the backside can then be solder attached to the next level, which would be a substrate. So what we want to do at SkyWater is we want to bring up the next generation of DECA M series, which is a generation 2, which has 2 micron lines and spaces and can accommodate a 20 micron IO die pitch. Next slide, please. So as we get into the fan-out wafer level technology, what's currently being practiced by DECA in Asia is the Gen 1. And this is really a 55 micron bond pitch, 8 micron lines and spaces, up to 2 micron layers. And you can see all the different variations there. Also, what's being currently practiced right now is the 1.5, which gets into a finer pitch, 45 micron die bond pad pitch with 5 micron lines and spaces and up to 5 micron layers. But what we want to do is get into the next, which is a Gen 2. And this is where we bring up this technology at SkyWater in Florida. And the exciting thing here is this is the state-of-the-art DECA M series, which gets into a 20 micron bond pad pitch with 2 micron lines and spaces. And we believe we can go greater than 5 micron, or excuse me, 5 layers of RDL on the surface. So the beauty of this is, as you can see, the ultra high density integration. And this is a technology we're aiming to get up and running in the late 2023, the most likely 2024 timeframe, to have that capability up at SkyWater in Kissimmee, Florida. So the interesting thing here is, in summary, our platform is focused on a 200 millimeter platform. So what we are right now is in the process of doing some early prototyping work with our suppliers to learn the process, with the intent of having a stronger learning point, such that when we bring up the process at SkyWater Florida, we're up and ready to start building hardware. So what's important here is you can see in these different configurations, the different types of structures that one can build. So the first one being a molded bridge die interposer. What's really important here, and part of SkyWater, we're involved with the ASIC consortium, but what we want to do is show that with the finer lines and finer line lines and spaces with the Deca technology, many of these designs could be built without a embedded bridge interposer. We just can accommodate that with the finer lines of spaces in the build-up structure on the top surface. But again, flexibility is there depending upon what the customer wants, we can do it. So the second iteration gets into deep trench capacitors embedded along with a bridge interposer in the core with chips last on the top side, and then that's attached to the next level of interposer. And then you could see there's many different variations of this type of interposer. The third one being chips first, system on a chip. And then the last one really gets into the ultimate, which is a chips first type of design with no bridge die. So a lot of different capabilities that one can accommodate with the Deca M series. On the right-hand side, you can just see the finer lines and spaces with the RDL structure, pre-UBM deposition. And then also you could see the on the figure below that, the actual M series through mold via. So you can see the embedded die on the left-hand side, but the plated through mold via connecting top RDL to the bottom RDL. Next slide, please. Another platform for the SkyWater is really the hybrid bonding. So SkyWater has licensed the ADIA oxide bond. Their trade name is called Zybond, and also the hybrid bond, their trade name is DBI. So right now we offer both these platforms at SkyWater, again on a 200 millimeter platform. We've shown success for both of these. Currently we are using a SUSE XPS 200 tool, which is ideally suited to do really high volume manufacturing for these two processes. The important thing right now with the hybrid bonding, we've shown that for a silicon-silicon wafer, we can achieve 100% bonding with a 4 micron pad, 8 micron pitch with the ADIA technology that we licensed. Next slide, please. So this just shows the XPS 200 bonding platform, which is really an ideal tool for this. So it's a single 6-axis robot with tool exchanger. So really the beauty of this, the wafer goes in there, gets treated with a plasma hydration, a nice tool to do proper alignment bonding. There's also a metrology a chamber in there to ensure proper alignment, such that if the wafers aren't properly aligned during the bonding, they can be reworked and realigned. And then after that, they're subsequently annealed to get the proper oxide bond, and then the extrusion of the copper into the surfaces. So this just clearly shows the stages of the XPS tool, but again, this is being currently practiced at SkyWater in our Florida facility, and we have shown success when we can do it with a silicon-silicon 200 millimeter platform for hybrid bonding and for oxide bonding. Next slide. If this just shows, matter of fact, this is one of the earlier examples that were just shown on the lower right-hand side, which is a 3+ micron pad on a 8 micron pitch. Matter of fact, the more recent examples show basically perfect alignment. So we've gone through learning, and we are much better now than we were before. So again, we have that capability, and we're ready to take on additional business in this area. Next slide. Part of the strategy we realized to complement our 3 platforms, which again are silicon interposer, fan out, and hybrid bonding, is really to offer wafer bumping. And there's a ubiquitous need for that onshore in the United States. And basically there's a lack of 300 millimeter capability. So currently we do not have this in SkyWater, but we have partners that we work with to bring up this capability and cooperate with us to do it for our our products, but we are looking at ways to either bring this into SkyWater or to continue our relationships with our partners for the bumping. And part of this would be to look at conventional tin lead, eutectic, and lead-free solder alloys. Next slide, please. And the key thing right now in the industry is back-end processes, assembly, and test. So, the key parts of the back-end processes are wafer thinning, dicing, temporary bond, debond, sort, and final inspection. So our strategy right now is we are in the process of identifying the equipment set to bring in those capabilities that really complements the three platforms I just got done talking about. And then we have companies engaged for advanced packaging to help us deal with other issues like variant substrate materials. So we will continue to have relationships to kind of feed the ecosystem for providing total assembly services for advanced packaging in the US. Part of our also future strategy is really to look at assembly capabilities for these advanced platforms, silicon interposers, and then also testing. This is going to be a very important part of the overall strategy, how to get a thin chiplet, known good die. How do we get that? How do we integrate that? Then how do we test it? So all these issues have to be sorted out, and we're in the process of working with partners to figure out what do we bring in and and who do we work with to get the solution for the future. So the key message here is that what we have to do is kind of create the ecosystem in the United States to provide these heterogeneous integration packages for our customers. Next slide, please. So keys to establish a domestic ecosystem. So here we have to have a consensus and priorities on the packaging and technology capabilities that need to be established. So this is where SkyWater, we are working with many people, mainly through these consortium. The one that Alan and I are working on right now actively is, of course, Scales with our UF partners, but also ASIC, which is being headed by IBM, to understand who does what, how does SkyWater play in this field. We're aligned very much with the US government to understand the defense industrial base needs, but then also talk with commercial customers to understand their needs. And this is going to be really important to figure out how do we balance our business, because if you really look at what's really driving this, what initiated a lot of this was the defense industrial base needed advanced packaging, and it didn't exist onshore. And that's why part of what our strategy right now in SkyWater is to fill that gap for the defense industrial base. At the same time, we're finding a lot of commercial interest. So, Alan, I don't know if you want to chime in here and add anything to this.
Yeah, one of the things that was kind of this domestic ecosystem picture is just kind of understanding the unique aspects that the U.S. is looking to put together here now, something that supports both the commercial and the government requirements here. And so we're kind of going back, and there's a lot of ideas that would remind people of like the old Cimatech model, where there's a lot of companies who are working together within an ecosystem and bringing specific technology capabilities to bear on this. The idea behind public-private partnerships is really strong right now, as the government is beginning to put a lot of investment into the private sector here, and how do we ensure that those investments are going to be leveraged and used appropriately? Well, it's nice to then have some sort of public-private type of partnership where you're aligned with private industry as well as public organizations like state and local governments, for example. Those are always good ideas. The other thing that we see is you have a very broad set of desires from the defense industrial base, for example, and understanding what their metrics look like going forward in terms of their program needs for the future. It's always kind of difficult because different programs, they all stay kind of decoupled from one another, and where you can begin to see how all of those needs become coalescing around particular technology spaces, that's an opportunity to then justify the expansion capability and the implementation of higher volume capacity technology providers. So we know that there is some work that has to be done over the course of the CHIPS program, just to kind of understand across all of the stakeholders, what is everybody's need going to be? How are these technologies going to, how are they going to evolve? What's going to take hold? What approaches and architectures are going to find the most applications to support? And so, at least from our perspective, you look at the CHIPS Act, this is a 5-year program. It's a good start, but you're going to spend 2 or 3 years in a lot of these programs implementing basic infrastructure capability, and then we're going to get to the point where we're really focusing on the establishment of higher volume opportunities. Okay, so that's the end of our presentation. I know we have some time for questions or discussions or comments. So, Woychik, I'll turn it back over to you.
All right, thank you very much, Alan and Chuck, for the very nice presentation. Now the session is open for question or comment from audience. You can raise your hand, or you can type in the chat and I can moderate. So one question from the chat is from the presentation. It is not clear where SkyWater capability sits comparative alternatives. Can you comment on that topic?
Yeah, so I can comment on that. So the 3 platform technologies that we're focused on today are the interposer technology space. Let's start with that one first. Right now, interposer supply is there's not a whole lot of people who are supplying that as a non-captive kind of component. So, for example, there's not a whole lot of companies that you can go to and just order an interposer, custom design, and get that as a consumable component. So that's one of the things that is unique to SkyWater's offering in this space, because we're not going to be selling our own products. We're a foundry business model company. So we intend to work in that space through the release of a PDK that customers can design into, that SkyWater can fabricate direct within the boundaries of that PDK to a customer spec. On the hybrid bonding side of things, for example, there are other companies who are engaged in hybrid bonding today, and a couple here in the US. There's not as many companies who offer that as a service, although there are a couple who do so. One of the things that SkyWater is doing is focusing its capabilities around 200 millimeter wafer sizes. So that's a bit of a departure from some of the things that have been done in the past. And that's going to continue to grow, I think, over the coming years. The need for higher or larger wafer size capabilities in hybrid bonding is going to continue to move forward. There's also going to be a need that's already identified for doing die to wafer. So one of the technology areas in hybrid bonding that we anticipate moving into in the future that's particularly well suited to the HI area is die to wafer hybrid bonding. You're beginning to see a few commercial applications in that space today. It's still pretty limited, but we believe that that's going to be a future direction where you see things like interposers and hybrid bonding and chiplet integration, for example, kind of coalescing. On the fan-out technologies today, there's really not a lot of other competitive capabilities here in the US. There are a couple of similar kind of approaches in fan-out, but at least in terms of fan-out wafer level packaging that's been demonstrated and launched at high volume capability globally, there's not another solution or provider that I'm aware of domestically. So that is going to be a relatively unique capability here in the US that will in some ways mirror what's happening in other parts of the world in larger volumes.
Okay, great. Thank you, Alan. So another question here is, any plan for thin film transport capability in your SkyWater site? Any plan?
Maybe we just need a little clarification. So thin film transfer would be for moving layers of thin film routing from one substrate to another.
I think so, yeah.
This was my question. So
Oh, okay.
basically, transferring thin films, the wafer level transfer of films, functional other than silicon, say lithium niobate.
Yeah, we don't have any plans for that today, Reza. You know, it's not to say that we won't be accommodating and looking at other material sets going forward. You know, the facility that we're in today is a silicon processing facility, and if you looked at it today, what it would look like primarily is a mature node silicon CMOS kind of processing capability without the CMOS, you know, transistor kind of stuff. So looking at things in different materials or different wafer sizes would be something for us to look at expansion in the future. And right now, at least for the time being, all of these technologies that we're talking about here are all going to be reliant primarily on silicon-based technologies.
Okay. Right. Thank you, Alan. All right. So another question is also probably related to optics. So can the photonic integrate the circuit playing the interposer technology? Can you comment on that?
Yeah, Jug, do you want to address that one?
Yeah, I think it can be depending upon the technology. Like for silicon interposer, it would fit in nicely because of the stability of the silicon and the flatness. So there's potential for it to play a big role there. Currently, we aren't addressing that. I think we're trying to get our base silicon interposer technology in order, and then we can look at different opportunities in the future. But it has potential to fit into that platform.
Right,
Yeah,
thank you.
I'll add to that, and I see the photonic aspects of packaging now being very, very crucial to the next generation of packaging here in the United States. I mean, over the course of my career, I've seen the photonic stuff kind of ebb and flow, and this is just over the last 2 or 3 years is the first time that it really felt like photonics was going to take hold and really establish itself in a number of different markets. Once we've established our baseline interposer technology capability, then I think this is an area that we would like to look at in the future in terms of how we partner with some other technology providers for maybe like the integration of photonic waveguides on interposer, or how we interface in other photonic connections and elements into you know, silicon based, where we're doing electrical to optical conversion and back and forth. So it's an area that I think we're interested in. There's nothing that we're doing today that is directly related to that effort, but as our interposer capability matures, I can see that becoming almost a virtual essential part of our platform capability in the future.
Okay, one question from Najmi. You raised your hand.
Yes. Thanks. Very nice presentation. My question is that about the characterization problem, excuse me, that you mentioned is very challenging. What is your plan on that? I mean, I've heard that NIST is like very focusing sorry, on that part. Could you also elaborate more about the characterization efforts for those techniques you are implementing? Thanks.
So do you mean the test characterization, electrical test?
Yeah,
characterization?
the interconnection characterization.
Yeah, that is something that we see. So SkyWater will plan on, I think, where we see our initial play in this is working within an ecosystem of people in the test area who have a lot of experience with that. So, you know, for example, if you are going to do a hybrid bonded heterogeneously integrated module, once you put those devices together and you have annealed them together, they are now permanently bonded to one another. But interfacing into that is not as straightforward as it would be if you were doing like wafer level test on a standard CMOS device, right? So the interface now into that device that you've done a hybrid stacking on is a lot more difficult than if you were just testing a single device alone. So We can see over time that our testing and characterization is probably going to be done with some ecosystem partners to begin with, and utilize some of the capabilities that they are currently developing. And then over time, as those solutions kind of mature and we begin to see where the market is driving specific architectures that we need to implement maybe a wider test facility for, then we might then start looking to bring in kind of analogous kind of wafer level test or module level test that you would do for standard packaging applications, but that will be considerably more complicated now because of the very high level of integration that's happening with these things, or the I/O interface dimensions being so dramatically different.
Yeah,
Thank
just
you.
to follow up on what Alan's saying is, like, for example, like in the fan out wafer level technology, bringing that up into SkyWater. So part of the strategy there is to have like daisy chain test vehicles. So these daisy chain test vehicles allows one to ensure that everything's going to be interconnected. So when you lay it out, you can calculate the actual conductivity. So when you do probe testing, you can probe it to make sure that the conductivity is what it's supposed to be. But more importantly, it's going to be a test vehicle to get the bugs out of the process, to understand the process, to make sure it's yield, but also to use that test vehicle to do like standard JEDEC reliability testing, to make sure you can pass critical tests like thermal cycle, temperature, humidity, bias, HASS, so on and so forth. So what we want to do as part of our strategy is going to be to have these test vehicles in different flavors and provide yield and also like thorough reliability test data to customers to show that they can meet this. So once you have that reliability data, then customers are very confident that you can then stick in the functional design and then do fully functional testing.
Thank you.
Thank
We
you.
have a few more questions, but we have a very limited time, so you can answer shortly. So then one question is about does SkyWater have a timeline for availability of the PDKs as a qualification complete?
We do. So
yeah.
for our, like the interposer PDK, so there is there's not a PDK so much as there is a design rule manual capability that we have today. So that's available under NDA with between us and our partners at Bridge, because that's a collaborative effort here. As we complete the qualification work on things like the hybrid bonding, which is a nearer term, sort of the end of 2023 kind of time frame for that, and for our fan out wafer level packaging, which is more of a 2024 kind of capability, we plan on having PDKs and design rule information that we can provide to customers. But there will always, I think, be in a lot of cases, particularly for those two technologies, some collaborative design work that we would need to do together.
Good. Thank you. Raji, are you there? So would you like to ask a question instead of for me to read your question?
Yeah, good afternoon. I hope you can hear me.
Yes.
Yeah, my question is, if universities are interested in working on small prototyping opportunities, obviously we can't subcontract at the large numbers, but less than 100K, can we co-develop technologies or prototypes? Are you entertaining that kind of, that level of collaborations?
We do envision that sort of thing, Raj. So SkyWater's business model is relatively unique in the foundry industry. So not only do we just provide standard processes that with PDKs that customers can interface into, we also engage with companies who are doing developmental activities in these spaces. So the idea is to utilize established process capabilities and then have the flexibility to add on to those some unique capabilities. So if you have program opportunities that are looking to engage, smaller prototyping kind of requirements, that's certainly the kind of thing that we would be willing to discuss.
Right. Thank you. So then besides the DoD, you have the defense contractor. Do you see other market where you think that your technology is a good fit? Can you comment?
Yeah, we do. So I think this is one of the keystone questions as we embark on this CHIPS program, right, and the reshoring of semiconductor manufacturing in the U.S. is, so what markets are going to be interested in the U.S. support, right? Well, there are things that, from a supply chain perspective, I think are very interesting for U.S.-based companies to want to have domestic supply chains for. So in the automotive space is one of them, and the medical device industry is one of them. There are also, I think, going to be opportunities that are going to be present here in the U.S. for things that are not like the high-scale consumer manufacturing opportunities, like cell phones, for example, but other industrial markets are certainly going to continue to want to look at pressing forward with a domestic supply chain of advanced packaged capabilities. And I think we see that, I don't expect that SkyWater is going to be making cell phone parts anytime soon, but there's a plethora of other markets like those I just described that I think fit very well domestically to begin with, right alongside what we see in the aerospace and defense.
Thank you. Volker, are you there? Right. One question from Volker is, first of all, great presentation. Are there thoughts to integrate lasers into the PIC?
I think there could be. Is this a reference to the fan-out technology then, and some of the pics that were shown there in that slide?
Okay.
If so, then perhaps. I mean, if in fan-out for optical components, it's a little bit more difficult to integrate optical devices and lasers into that, because obviously the device is fully encapsulated, right? So we're not currently thinking about how we would be able to embed and then provide an optical pathway for lasers or other optical components. But you could certainly envision them being incorporated into a fan-out module on the top in some way, so that now you have a transmission path that's not being blocked.
Thank you. Volker, do you have a follow-up question? Thank you.
No, thank you very much. Exactly, because thank you, Alan. Exactly, because actually Tower Semiconductors just today or yesterday actually announced that they actually also want to integrate a 3.5 laser into the SiPho, silicon photonics process, and would be certainly interesting to explore. This is something we do right now a bit on the prototyping side, academically, using these photonic wire bonds, but really in more sort of monolithic integration into a process would be really the way to go, I guess, down the road. So we're very exciting, interested to maybe explore this even jointly or so, or down the road. Thank you.
Yeah, I think there's going to be, we're literally at the beginning of a lot of things here in the U.S., and SkyWater is at the beginning of a lot of things too. So the ideas for how new technologies that are being developed in the universities and small companies, and how SkyWater can collaborate with those companies, that is part of a bedrock kind of our business model that exists even in our CMOS foundry today, and is going to proliferate into what we're doing in the advanced packaging space. So we're definitely interested in those discussions.
Great, looking forward. Thank you.
Thank you. Yeah, definitely this video will be available through SCARE's website, and I think that we pretty much have only 1 minute. If there is no more question, then let's thank our speaker again. Thank you very much, Alan and Chuck.
You're welcome.
So we will conclude our first webinar series. Thank you very much for coming.
Thank you, Woychik, for having us. Appreciate it.
Yeah, bye now. See you guys.